Hello. In Chapter 14, Lecture 9, we're going to go over two topics. We're going to look at reaction mechanisms and we're going to look at catalysts. Okay, so in this pre-lecture video, we're going to go briefly over what both of them are so you guys are ready for class. And then if you want to watch the reaction mechanism video and the catalysis video, you can get a more in-depth picture of what's going on, along with the practice problem videos that are on there as well. Okay, so when we talk about a reaction, we almost always talk about it in terms of an overall reaction. So an overall reaction is reactants and products, and doesn't show what's going on in the middle of the reaction. So it doesn't show the transition states or intermediates, any intermediate species, and it doesn't show how our catalyst is included in a reaction if we have one. Okay, so today we're going to look at what's called a reaction mechanism, which has all the steps of a reaction. So to think that a reaction occurs in one simple step is incorrect. Here with our reaction mechanism, we look at what we believe theoretically occurs, and this is based on experimental evidence, specifically looking at stuff like your rate law, and looking at things like what species are being produced during the reaction. Okay, so reaction mechanisms are a series of elementary steps, and these steps are based on our rate law. So in theory, we're showing the actual collisions that are going on. Okay. Each of these elementary steps, those collisions show how many molecules are actually participating in each step. So we have something that's called molecularity, which tells us how many reactants are involved in a particular step of an elementary step, or particular elementary step. So this is basically how many atoms are or how many molecules are colliding at one time. Okay, and we're going to have three different molecularities we will look at. We have unimolecular. This is one molecule in the elementary step. So the rate for that would be equal to Ka. So a unimolecular elementary step is a first order elementary step. Okay. Then we have bimolecular. Here we have 2 molecules involved in the elementary step. So our rate would be equal to Ka squared, or rate would be equal to Ka B. But in general, we'd still consider this to be a secondary elementary step. And lastly, we have termolecular. So we have 3 molecules. In the elementary step. So 3 molecules are colliding at the same time during this elementary step. So here our rate could be Ka cubed, or it could be Ka squared B, or Ka B squared. Right? But again, this is going to be a third order and we're going to call this second order. Third order elementary step. Because we're showing our actual collisions with our elementary steps, we can base our overall rate law on the slow step of our reaction mechanism. So because the elementary steps show the actual collisions that are involved, in a given step, you can determine a reaction's rate law based on the slow step elementary step of a reaction mechanism. Okay. So with the reaction mechanisms, we're going to have 2 or more elementary steps involved. And with each one of those, they're going to have their own separate activation energies. And they're going to have intermediates that we don't see within a regular overall reaction. With the overall reaction, we look at the energy of the reactants, we look at the energy of the products, and the activation energy is just kind of like a combination of all the activation energies of all of our elementary steps, but with a mechanism where we're actually showing the different steps, the different collisions, we have fast and slow steps within. So let's take just kind of a theoretical idea of a reaction mechanism. So let's say we have something like, and actually I have an actual reaction mechanism we could do. So we have NO2 gas plus NO2 gas reacts to produce NO3 gas plus NO gas. Then after that occurs, so this is our first elementary step. I'm just going to do ES for elementary step. And then our second elementary step would be NO3 gas plus CO gas reacts to produce NO2 gas plus CO2 gas. Okay, so this is our first and second elementary step. And our overall reaction, we're going to take anything that is on both sides of a reaction, we will cancel out. So this, actually, this right here cancels out this. This right here cancels out this. And then we have everything else. Nothing else cancels out. So our overall, what we generally would see is NO2 gas plus CO gas reacts to produce NO gas plus CO2 gas. And this overall reaction does not show the full picture, right? Our elementary steps show us our full picture. And with any reaction mechanism, you'll be told information about your activation energies by showing whether a step is considered fast or slow. So here, this first step would be considered our slow step, and the second one would be considered our fast step. Okay? And like I said, you'll either be given which one's your slow and your fast step, or you'll be given information to determine that. So for instance, I could also determine which one is my fast or slow step based on the energy profile of the reaction. So we have reaction progress versus potential energy. Okay, so we start out with our reactants. In this case, it's NO2, two NO2s. And then we get up to what's called a transition state. And then we produce our first intermediate, which in this case is NO3 and NO. Okay? Or actually, I lied. It's just NO3. Okay? And then we have a second activation energy, and then we produce our products, which are going to be CO2 and NO. Actually, let's do our actual reactants here. So this is NO2 plus CO. And then, sorry. So our intermediate is going to be this species right here. So an intermediate is a species that is created in one elementary step and then consumed in another. Okay? So the reaction progress diagram would look like this. We can tell that the first step is our slow step because it has the greatest activation energy. So that activation energy there is greater than our second step's activation energy. So we call our slow step, and there's only going to be ever one, we call it the rate limiting step. So it will determine how long our rate, or how long our reaction takes. Okay. It's going to have the greatest activation energy of any of the elementary steps. And it's going to slow the reaction and determine the rate. So our overall reactions rate law is based on the slow steps molecularity. So for this reaction above, we have 2 molecules of NO2 that is reacting, so our rate would be KNO2 squared. So this would be a second order process with respects to NO2 and second order process overall. So this would be the rate for this reaction. In class, we'll also look at additional, I'll do a couple of examples of determining our rate law based on our elementary steps. Because if you have your initial step being your slow step, it's pretty easy. If it is not, it becomes a little more complicated. And I did do an additional couple of examples of that in a further video. But watch that to make sure you understand what's going on if your first step is not your slow step. If your second step or your third step or your slow step, it gets a little bit more complicated. You also see a catalyst in a reaction mechanism. And with that, it is going to be consumed in a step and then reproduced in a further step. So a catalyst is a substance that is not consumed during reaction, but it does speed up the reaction by giving us another path for our reaction to take. Which is why it is reproduced or regenerated. So a lot of catalysts you can actually get back at the end of the reaction. Okay, so we have our catalyst. We're going to look a little bit more at catalysis, not very much, but catalysts can be homogeneous or heterogeneous. If it is homogeneous, it's going to be the same state as the reactants. If it is heterogeneous, it's going to be a different state. Okay. Catalysts are generally going to be either metals or maybe a carbon compound, something that allows the flow of electrons, or an enzyme. So generally metals or enzymes. With enzymes, it's a protein. So it's a huge macromolecule It has what's called specificity, which I'll talk a little bit more about later. But our metals, they're going to be able to basically attach to our compounds and then provide electrons when need be. With our enzymes, our proteins, they're going to attach to our compounds and put things in the correct orientation for reactions. Okay? And most biological processes would not occur without enzymes present because their rates are just too great. Or sorry, their activation energies are too great. Okay, so that's it. That is what we'll be going over today, or in the next lecture. If you guys have any questions, let me know. Have a great day. Bye!